arrangement, crystal field splitting is so low that it cannot compete with the pairing energy. Pairing energy can never be overcome by the crystal field splitting. So all tetrahedral complexes are high spin. Up till now, probably only one tetrahedral complex with low spin has been arranged. So we can safely say has been obtained. So we can safely say that for all practical purposes, there is no low spin tetrahedral complex, and all tetrahedral complexes are high spin. And if someone asks you what is the reason is that high spin or low spin case arise when a low spin case will arise when 10 DQ, the crystal field splitting will be much larger than the pairing energy. So that means crystal field splitting must be sufficiently large. But for tetrahedral complexes, since none of the d orbitals approach the ligand close enough, so the crystal field splitting is much lower, even less than 50% of the octahedral complexes. And as a result of this, you will find no ligand which can cause sufficient splitting to overcome the pairing energy. And as a result of this, tetrahedral complexes are always high spin and no low spin tetrahedral complex are known, right? Except one. So that is an exception, we can forget it. Now we come to application of crystal fields splitting, and this is very important. Crystal field detect. This is we are talking about this very important parameter called octahedral site preference energy, or some books call it octahedral site stabilization energy. So either octahedral site preference energy or octahedral site stabilization energy. What is octahedral site stabilization energy, or what is octahedral site preference energy? It is the difference in the crystal field stabilization energy between an octahedral complex and a tetrahedral complex of the same ligand. That means we consider any particular ligand for a given metal atom or metal ion, and we calculate what will be the CFAC if the ligands occupy an octahedral symmetry. And we also calculate what is the CFAC if the ligands occupy or goes to a tetrahedral geometry, and we take the difference of the CFAC between the octahedral site and the tetrahedral site, and the energy difference is called octahedral site stabilization energy. As I have told you, that in most of the cases, since the splitting of the tetrahedral case is much lower than the octahedral, so whenever there is crystal field stabilization, so there will be invariably octahedral site will have higher crystal field stabilization energy than the tetrahedral sites, but the energy difference will vary from case to case. So I repeat, what is octahedral site preference energy or octahedral site stabilization energy? Or we can write it here. So we may write O is the octahedral site stabilization energy or octahedral site preference energy. It is equal to CFAC for the octahedral site minus CFAC for the tetrahedral site, right? Now usually this value is either 0 or positive. 0 is when there is no, for instance, if you have a D0 system, it has got no crystal field stabilization either in the octahedral or tetrahedral field. Similarly, so for D0, for D5, again, we will find for D5, all d orbitals are occupied. D5 high spin, obviously, for at least for octahedral, it may be high spin, low spin. For D5 high spin, again, there can be no crystal field stabilization energy, because the amount of stabilization of the T2 orbital is actually matched by the amount of destabilization of the E orbital for the octahedral, and reverse in the case of tetrahedral case. So D0, D5 and D10. These three cases has got zero CFSE both in case of octahedral and tetrahedral. So for them there will be no difference, right? There is no octahedral side stabilization energy is zero. That is, it has got no preference for either octahedron or tetrahedron. Now, for any other system other than D0, D5, D10, that means D1 to D4, right? So positive will be from D1 to D4, you will get a positive value. And again, from D6 to D9, you will get a positive value. So invariably, octahedral site is more stable than the tetrahedral. But question is that the energy difference, how much positive, that means how much stability is there. So depending on certain circumstances that you will find, we should learn that for some of the configuration the positive value is quite large. That means octahedral side is much more stabilized compared to tetrahedral, and so there is almost no chance of obtaining in tetrahedral complex. But there may be certain configurations where the difference is relatively small, and so there will be under certain conditions, depending on the solvent, depending on the steric bulk of the ligand, which may change this small positive value, right? Which may overcome this small positive stabilization in favor of the octahedral complex, and you may get tetrahedral complex. So question is, which are the systems which are likely to show tetrahedral configurations, and which are the systems which are most unlikely to show tetrahedral configuration. So let us try to see for that. Now here in this table, again, this table has been taken from Hui-Kaiter's book. So what is done here, that from D1 to D9 system, we have taken different metal ion, and for some systems we have, for instance, for D3 we have divalent metal ion as well as trivalent metal ion. Here we have divalent metal ion as well as trivalent metal ion, and as expected, as we go from divalent to trivalent, crystal field stabilization energy increases, right? And so invariably OS-AC for the trivalent metal ion will be much higher than the divalent metal ion. But in general, we shall talk about the divalent metal ion. So we have first of all considered the metal ions, defined metal ions. What is the configuration in the octahedral crystal field? What is the configuration in the tetrahedral crystal field? And then we have written here delta O, that is the octahedral crystal field splitting. This is obtained experimentally. We are talking for each of these metal ions, we are considering the aqua ligand. Ligand is constant, and that is water, right? So we are considering aqua complexes. So here we have data for the delta O value experimentally obtained from the spectroscopy. What are the delta O crystal field, octahedral crystal field splitting for each of the complexes? And then we have tabulated the corresponding delta T value. Now, whereas delta O values are obtained experimentally, delta T values are not experimental values, but delta T is a theoretically calculated value using this formula, delta T equal to 49 delta O. So here we have experimentally obtained delta O value. Here we have the theoretically calculated delta T value, that means the crystal field splitting in presence of a tetrahedral ligand symmetry, right, using this formula delta T equal to 49 delta O. And then we have taken the difference between them and converted. Here the data is in centimeter inverse, and we have converted the CFAC in the corresponding kilojoule per mole, right? So after calculating the energy of the system, then we have converted it to the kilojoule per mole. So we have converted into kilojoule per mole in the octahedral field and tetrahedral field, and then we have calculated the OS-AC, which is the CFAC in the octahedral field minus CFAC in the tetrahedral field. Now, going one by one. So for now, D1 system, D1 number of electron, D electron 1, we have T2G1 or E1 configuration. For octahedral, it is T2G1. For tetrahedral, it is E1. And then, if we calculate the CFSE, it will be 96.2 and 64.1. So difference is 32.1. Then, if we go to D2, we find the difference in the divalent metal ion, or rather here we are considering trivalent metal ion. So difference in the trivalent metal ion. So let us talk about all trivalent metal ion. So if I take the trivalent metal ion, the difference is 190 minus 127, 64. Then if we go to D3, we have divalent as well as trivalent. Since we have taken the trivalent, so let us go to the trivalent. So it is equal to 176. So to be consistent, let us consider only the trivalent systems, or in some cases we may have divalent ion also. So okay, 122 and 176, 122 for the divalent metal ion and 176 for the trivalent metal ion. Now next we go to the D4 system. Again, we have a divalent and trivalent metal ion. Sorry. For the divalent metal ion, we find it is 71, and for the trivalent metal ion, we find it is slightly higher. It is 106. Right. Then we go to D5. Obviously, it is 0. Right. Whether it is divalent or trivalent, it is 0. There is no stabilization. If I go to D6, again you may have a divalent or trivalent. For the divalent metal ion, the value is 14.8. For the trivalent metal ion, we don't have any data because cobalt 3 hexaco is actually low spin complex, but since all of the complexes here we are considering the high spin complex to avoid the calculation of pairing energy. So for cobalt 3 we are not tabulating the data because it is a low spin complex, whereas the all other aquo complexes are high spin complex. So if I go to cobalt 2, right, cobalt 2, it is D7, the value is 29.3. If I go to nickel 2, which is D8, the value is 86, the OSS is 86, and then D9, the value is 60.6, and D10 again it will be 0. So if you look at this table, you find that first of all, as I have told you, for D0, D5 and D10, there is no stabilization. Okay. So here, therefore, D0, D5 and D10, you can have equal possibility of having octahedral and tetrahedral complexes. So depending on the condition, depending on the nature of the ligand, either you may go get tetrahedral complex or octahedral complex. But for D1, D2, D3, D4, D5, D6, D7, D8, D9, these complexes, everywhere OSS is more positive. OSS is positive. That means octahedral side is preferred. But the amount of preference is not always very high. We find for D1, we find it is quite low, 32. For D2, at least for D2, here we find it is 64. So for D1 and D2, this value is not very large, right? But for D3, this value appreciably increases. So obviously, there is no chance of getting any tetrahedral complex here. For D4, again, as we find, for D4, for divalent metal ion, it is 71. For the trivalent, 106. So for D4, it is not very large, but it is not very small. For D6, we find the gap is quite low. So that means there is every chance of getting that tetrahedral complex, right? For D7, again, the gap is positive, but it is not very high. And then for D8 and D9, again, it is quite high. So if I try to tabulate what are the metal ions that are or configurations that are likely to give tetrahedral complexes, we may say D0, D5 and D10 has the highest possibility. And then you find D6 has got the lowest OSSE. So D6 has got a high possibility of giving tetrahedral complex, right? Then D1 has got very low value, quite. So D1 has got the possibility. And then D7 again value is not very high. D7 29.3. D7 has got again quite high probability of giving tetrahedral complex. And for D2 particularly D2 we can say 64. So again the value is intermediate. So you can have some chance of getting tetrahedral complex here. So this is more nicely illustrated uh, in this diagram here. So the this blue line correspond to octahedral site stabilization energy of the octahedral site stabilization, or rather these blue lines correspond to CFSE for the octahedral complex, and this violet line corresponds to the CFSE for the tetrahedral complex, right? And their gap is obviously the octahedral site stabilization energy. So you can see for D0, D5, and D10, the octahedral site reference energy is 0. So you can have very high probability of getting the both octahedral and tetrahedral complex. Now, if I go to D1, so this is the octahedral part, this is the tetrahedral part. So gap between octahedral and tetrahedral CFSE is low. So for D1, we'll have high chance of getting tetrahedral complex with appropriate ligand. For D2, the gap is much more than that of D1 or some other cases, but again the gap is not very large. For D3, as you can see, this is the octahedral, this is a tetrahedral, so gap is very large. So you may say there is very little possibility of getting tetrahedral complex with D3. Now for D4, again the gap is quite large. This is D4, gap is quite large. So for D4 also there is very little possibility of getting tetrahedral complex because octahedral is hugely stabilized. Then if I go to D6, again the gap is quite small, almost similar to that of the D1, right? So here we have a high probability of getting the tetrahedral complex. And again, if I go to D7, you have this gap, right? So it is almost similar to that of the D2, and again you will have possibility of getting the tetrahedral complex, right? And if I go to D8, so gap is from here to here, quite large gap. So you should not expect any tetrahedral complex for D8, right? At least with the moderate field ligand. And then we have the D9, again gap is quite large. So from this diagram also it is clear that apart from D0, D5 and D10, more likely tetrahedral complex will be formed with D1, then D6, D1, D6 most probability, and then we have the D2 and D7 also to some extent, but their energy gap is much larger compared to the say D1 or D6. So most likely it will be D1 and D6, right? And there will be some chance of getting from D2 and D7. For D8, for other configurations, it will be very difficult to get tetrahedral complex. But in reality, we get sometimes tetrahedral complexes depending on the circumstances. For instance, for nickel itself, if we have chloride, very weak field ligand like halides, we get some tetrahedral complexes. We get octahedral as well as tetrahedral complex depending on the condition. For nickel tetrachloride is very well known. It is a tetrahedral complex. Nickel tetrabromide is a tetrahedral complex. So it is not that we do not get, but we have to adjust the condition, and sometimes you have to use a very weak field ligand to get sometimes the tetrahedral complex. But in general, this diagram tells you, this diagram as well as this tells you that apart from D0, D5 and D10, you will have very good possibility of getting tetrahedral complex with ligands which has got crystal field comparable to water. So remember, we are considering water as the crystal, water as the ligand. So if you have a much more weaker ligand than water, then the values will somewhat will change. We are talking about the water ligand, aqua ligand. So oxygen with oxygen containing ligand, D1 you will have quite good possibility of getting tetrahedral complex, right? Then D6 will have quite high possibility, and to some extent with D2 and D2 and D7, D2 and D7 also, D1 and D2 most likely, and to some extent D7 and D2 also we may have tetrahedral complex, right? But for the other metal ions, if you have ligand comparable to crystal field strength of water, you will have very remote chance of getting tetrahedral complex. But if you can adjust the ligands to much weaker field, like say fluoride, halide, then in some cases you may get tetrahedral complex. And as I am giving you the example that for instance nickel, right? Nickel 2 plus, it is D8. So if you have nickel hexaco, it is always octahedral. On the other hand, if I take very weak field ligand, say tetrachloride, which is much weaker ligand field than water, then nickel tetrachloride or nickel tetrabromide, these are tetrahedral, right? So remember, these data, this table or this table or this diagram, this is valid mainly for the high spin. We are comparing first of all a high spin octahedral system with the tetrahedral system, and our ligand is crystal field of the ligand is assumed to be similar to that of water. So if you have a much weaker field ligand, then this gap may change, and as a result of this, sometimes you may get tetrahedral complexes with other metal ions also. This is the classical case. And again, if I take for instance D6 cobalt 3, right? Cobalt 3, I have told you we have no data, right? For cobalt 3 we have no data, but some of you may know that if I take cobalt chloride, cobalt, we are talking about cobalt 2. So D7, I have told you D7, there is good possibility of getting tetrahedral. Now cobalt 2, in the crystal, you will get cobalt 2 6H2. And these crystals are pink in color, right? If you dissolve in water, so in crystal it exists as this, and if you dissolve in water, then the aqueous solution is also pink in color, right? The reason in both cases why it is pink, because in both cases you have really a octahedral cobalt 2 ion surrounded by and the two anions, 2x minus, that is the two halide ions, are in the outer sphere. So whether you dissolve it in water or in crystal, cobalt chloride 6H2O is actually an octahedral complex, and that's why it is pink in color. But if you take the same cobalt chloride and dissolve it dissolve it in concentrated HCl or in alcohol, you will find that the solution is blue in color. The reason is that in presence of concentrated HCl or alcohol, what happens? Cobalt is converted to COCl4 minus, right? This ion. So this is now tetrahedral, and that's why it is blue in color, right? That's why it is blue in color. So cobalt in octahedral when it is in octahedral geometry with ligand field strength of water, cobalt 2, we are talking about cobalt 2. When it is with ligand field such as water or stronger field ligand, it becomes octahedral and it is pink in color. But with chloride like ligand, right, it gives tetrahedral. And you know, this phenomena of transformation of cobalt from tetrahedral to square planar and color changing from blue to pink is actually used in silica gel. Some of you as a silica gel as a drying agent, you will find in some medicines they give silica gel. when you keep your camera lenses or some sophisticated electronic equipments, you sometimes add silica gel. Now in silica gel, what happens? You have silica, and then to the silica you add some amount of cobalt 2 ion. Now when the system is dry, cobalt 2 is sitting in the same geometry as the silicon, and cobalt 2 is tetrahedrally surrounded by 4 oxygen atoms, and that's why it is blue. So when silica gel is dry, then because there are no aqueous ligand, cobalt 2 will be tetrahedrally surrounded by 4 oxygen atoms of silicon, 4 oxygen atom of silica, and so it will be blue in color. But when the moisture is absorbed, right, when silica absorb the moisture and water goes into the lattice, then immediately this blue cobalt 2 is converted to a pink cobalt hexaco ion, and so the silica gel turns from blue to pink, and that indicates that your silica gel has lost its ability to absorb moisture, and then you have to again dry the silica gel in a oven at 110 degrees centigrade for few hours to drive out the water and get back the silica gel. So this property of cobalt, that when it is in tetrahedral geometry it is blue, when it is in the octahedral geometry it is pink, is used for indication of the presence of moisture. So in the silica gel you add some amount of cobalt ion. In dry atmosphere, this cobalt 2 doped silica gel will look like blue in color, but with time, as it absorbs moisture, gradually this blue color is transformed to the pink color, and when it goes to the pink color, that means silica gel has lost its ability to absorb moisture, because it has been cobalt 2 has been converted by absorbing moisture to cobalt hexaco pink color. And then you need to again dry the silica gel by heating it in an oven for 110 to 120 degrees centigrade for few hours. You will find again the moisture has gone and the silica has turned blue, and so you, after cooling, you can use that silica gel again. So this is the thing. So in the next class we shall take up the spinels and other uses of CFSE. Thank you.
Thank you, sir.
Okay, I'm leaving.